So today, we also want us to look at this topic before us together. We are looking at optimized industrial earthing system designed for compacted clay-like and stony soil condition. Is a kind of customized area of earthing that we want to look at. But before we do that, we also look at the general scenario of earthing. Like the moderator said earlier, this is part of electrical engineering that is very, very important. And also, if you look at it today, beyond this electrical installation, electrical gadgets, everything around us now is tending towards smartness, towards automation. The phone, the wristwatch, even the toilet seat, everyone is automated. And all of these gadgets cannot work without electricity, be it DC or AC, direct voltage or alternating current. All of these, direct current or alternating current, all of these tend to either jeopardize or affect as a trap to our existence if they are not well managed. Washing machine, freezer, anything, gadgets in the house, gadgets in the industry, the chiller, the compressor, all those gadgets can, as they are very, very useful to us, they can at the same time be a kind of trap that can lead to death. So that is why this is very, very important. So in the introduction of it, we said the general earthing system connects different parts of electrical installation with the surface conductor of the earth to be able to guarantee security and protection of life. As we know, earthing is connecting electrical part, metal parts of gadgets into the Earth's surface. And why do we need this earthing? This is very, very important. We need to, as said earlier, earthing is to personally protect us. Personnel safety. Who is the personnel? Anyone that use gadgets, anyone that use any equipment, devices that is connected to a source of electrical power, that person is a personnel, and that person can be open to danger. This will lead me to share some of the experiences that I had concerning this aspect, this safety of whoever that is using electrical gadgets, and how important is to earth all metal parts of those gadgets. Sometimes ago, many years, in my grandfather's house, there was this accident that happened. The supply cable that supplied the house with the single phase in that house was passed through the facer board, and the roofing sheet, that is corrugated iron sheet, was touching that wire. Over the time, as the wind was blowing here and there, blowing the wire, part of the insulator of that conductor was cut, and there was current on that roof, and we don't know. And eventually, one evening, one young woman want to go and take his bath, one of the tenants, and as was like, she need to shower before sleeping, and she doesn't want to go and use the bath. She went to the side of the house in the night, tried to shower. Remember, before showering, she was on her slippers. The ground was dry, slippers was dry, her body was dry. He just removed her wrapper, throw it onto the lower part of the roof. And after showering, he would now want to take the wrapper and go to sleep quietly. This time around, the ground was wet, the slippers was wet, she too also was wet. As she touched that wrapper, she received electric shock. As she fell down on the ground, she shouted, and some people went to rescue her. And that was a signal at the back of my mind since then. I think I should be in primary school that time. Many years after, I also personally encountered something that will have claimed my life. I was at Race Cross, we were walking, and the scaffold was like 7 meters to 8 meters, about 28 feet from ground. And the panel that we were working on was up there. And some of my colleagues that were working on those panels, they disconnected the earthing wire on the panel body without considering the effects and the danger it might pose. So they just look like we have the current, we have the voltage that we need, and the equipment is working. So when that equipment had faults, they were trying to sort it. They couldn't get that done. Then I have to climb the scaffold to go there, not knowing that they've removed the earth wire. As I climbed, put my head in the cabinet because it's a big cabinet. My hand touched the earth wire of that cabinet. That's how I received electric shock. And it was so terrible. I considered that if I tried to jump, it was too high. I might lose my spinal cord. I was trying to endure the shock. I couldn't. I was trying to shout. My voice was not going up any longer. And it was a very difficult and terrible situation until one young guy, Demola, that just look up to see if I have been able to resolve the fault on that panel. He discovered that I was struggling with my life there. He quickly ran to the breaker. He switched it off and also removed the industrial socket. That is how I was able to be rescued. So personal safety is very, very important when it's come to electric shock. Also to protect equipment. Earthing protect equipment. If equipment is well earthed, it will give them desirable long life. But if not, it can compromise their efficiency, lightning and such. These are natural phenomena that nobody can stop from happening. When the atmosphere is charged electrically and electrons are flying up and down, then there is spark in the sky and the lightning comes. And this also affects our installation. If the house, if the factory, if the industry is not well heated, definitely those equipment there might receive fault currents, which will also compromise their service life, system stability. This is very key. Even in electronics, for the system to be stable, the panel, the device must be well heated. If they are not well heated, as we go about carrying them, our body that is having static current, our clothes that is having static current, our hair that is having static current can compromise the semiconductor. So this earthing, in summary, it protects our life, protects equipment. It also saves our gadget and our life from lightning, and also it stabilizes our system for us. So if we are looking at earthing, we have three major generations of earthing. The first one is conventional earthing. This is traditional earthing that everybody around is used to. This is the one they know. What is that? You have a big pit that is dug, and in that pit, you put copper plates, or you even put an iron rod in it, and then you put salt and charcoal. This alone has saved a lot of life, has been so wonderful in that generation, because that generation, the gadgets were not many. It's only the electrical part that was there. And how many households have so many equipment? So they use this thing wonderfully well at that time. But as time goes, we discovered that this cannot do enough. For us to have a proper and a good earthing, the value of the resistance must not be more than 5 ohms. In some other aspect of our work in telecommunication, it is even less than 1 ohm. If it's up to 1 ohm, it can damage those equipment. But in those days, all those communication lines are not there. So it is conventional earthing that was done that time. As we progress, I will show us picture of that. As the time goes, we come to another phase of generation where we have chemical earthing. This chemical earthing, as you can see here, we are seeing the compound. It could be salt, it could be some of these compounds mixed together with soil and water. Then we see that it also reduce the resistivity of the soil and improve our earthing. But this comes with challenges. It comes with this limitation. The chemical, at the end of the day, when it dissolved, it caused a lot of problem to the water body under the ground, because it tend to lynch. It percolated the soil and leach into the body of water underground, and it compromised our drinkable water, be it borehole or well. Those chemicals mix with it also contaminate and pollute our soil. Anything you plant around that place is like when you are in Niger Delta and the vegetation begin to become yellowish because of the reaction of those chemicals. It has its own limitation. But what we are looking at today, to optimize industrial earthing system in this design, we go to the generation 5, which is using gen. In generation 5, we are no longer depending on only charcoal. We are no longer depending on only salt. We now have ground enhancement materials. It is combination of aggregates combined together that can suit every kind of soil, not only one particular soil now. Every kind of soil, it can suit the position, the situation. And this comes with a lot of advantage. One of it is extreme low resistivity. If you mix the gem very well with cement, and why do we need to mix with cement? Because we want it to be compacted, to be like concrete around the metal, around the maybe the copper rod, around the steel rod that we are using for the earthing. When it's there permanently. It's not losing out. It gives a longevity of the earthing system. And when you do that, you discover that in this 5th generation of earthing, there is no corrosive, because the aggregate was well measured, well balanced, is calculated. It's not like the other 2nd generation and even the conventional, that when the salt reacts with iron, it gets it corroded, and then you need to go back again for replacement. But in this generation 5, you don't really need to worry about corrosive nature of this material, because it won't corrode. And again, it is permanent and maintenance free, because it's like rock there, and is also environmentally safe, is inert. It doesn't leach, it doesn't compromise the soil for vegetation. So this is what is important, that we need to also take note in earthing. But is it the same cost effective? Like when you are looking at the cost price of doing this and doing that of generation 1, no, it is not the same. But at the end of the day, by the time we come to the end of this webinar, you will see that it's worth it. It makes sense that you may spend so much now to do industrial earthing. Instead of spending like 10,000 naira, you are going to spend like 1.2, 1.5 million to get it done. But it's worth it. It is going to save life, it's going to save equipment, and it's going to save the environment. This is the some of the picture that I mentioned. The one at the left is the normal conventional earthing. The rod is here, the pit is dug, and then the copper wire is also connected to it straight to earthen bar, where every other equipment will take their lead. Also, this is the chemical you can see here. This is the salt mix, the chemical mixed together to give enhancement to the soil around this place. Now, the most important part of this webinar this afternoon is this, and I want us to pay much attention to it. Is why the soil tests. Many of us make this mistake. Immediately we are giving this installation, we straight away give code for the earthing, and we just look at it lightly. But many of us, we have burnt our hand because of this mistake. And that is why I also want us to pay attention and to look at it very well. Why this earth? Earth is as an electrical conductor with unpredictable characteristics. The resistance of an earth connection varies. Why? Earth has a lot of composition. The chemical content are different. If you come to this geographical area, you see that the chemical, the mineral you see, the compound you see in the soil is different from another area. The moisture content of the soil are not the same. Temperature are not the same. The season, now the season also in the year change a lot of things concerning the soil. Why is soil so important in earthing? Soil has been our friend, and he has always been our protector. As the religious body book says, that we come from the soil, and from the soil we go. Most of what we use, if not all, they are from the soil. Is it paper? Is it the iron? Is it the mineral? Everything is from the soil. The food that we eat, we all depend on the soil. So this soil also has determined to deliver and save us from fault current. The fault current that comes from any error of fault in the industry, or maybe the lighting, is say, I am here, I can accommodate, like in chemistry or biology, they said gases move from the region of higher concentration to the region of lower concentration. So also the current. Current will move from the source to a part that is having less resistance to its flow. That is where it will go. Then we now look at this land, this soil, this earth is abundant around us and is ready to accommodate all this excess current. And why, again, do we need to depend on earth to be able to get this done? If you look at our equipment in the industry, let's, for example, look at a panel, electrical panel, or look at a motor of maybe 15 horsepower that is driving a conversion, or you look at a chiller or a compressor in the industry. All of them are not at the same potential. And when the potential are not the same, current flows, then there will be potential different. There will be a fault voltage in between the line. So ground, the earth, is what is now providing a level environment for all the equipment. So if equipment A is connected to the ground, equipment B is connected to the ground, all of them at the end of the day, we nearly share the same potential, so that at the end of the day, everything will loop together and form a kind of network around the earth. So that's the reason why we send all connection to this earth, to this ground. Now, we agree that the earth is ready to accommodate and is going to assist us in removing all this excess current. At the same time, we now need to study this soil very well so that we will not have problem. Remember, what we want to do is to create a part that is having a very less resistive part. That is, the resistivity of that body where we want to send all this essence current to must be very low. So if we are going to achieve that, then we need to study, we need to know, we need to calculate what is the existing resistivity of that soil, whether it's going to pose a danger. Because if the resistivity is high, that is the resistance of the soil is higher than you as a personnel that or the equipment that is connected, the fault current, instead of going to that ground, will return back to that personnel or to that equipment, which may cause harm, cause death, or cause damage to that equipment. So we need, let's go further. Now, what do we need to study here? We need to now look at the constituents of the soil. And as we go, you see why that is important. When you look at the compound, the silicon dioxide is a kind of quartz and silicate. And main component of it is clay and iron oxide. You see all of these and the pH that is there. Because of our time, let's go to the next one. So the clay material, this is, pay attention to this, is important. Now, kaolinite. If you look at this kaolinite, under the description here, you see that it's a non-expanding and stable. This one does not expand, but is stable. Multimorillite, the semic. This one, it expands and it has high water absorption. Remember, for us to be able to achieve a better earthing environment, moisture is key, is important. It helps increasing the conductivity of the soil. So this particular clay type of soil, it absorbs water to itself, not like the first one. And when you see the highlight is non-expanding, but is rich in potassium. Chlorite is more common in deep clay. All these are very important because what we are going to use at the end of the day for the optimization depends on all of these chemicals to be able to achieve that environment of low resistance that we are looking for. So in summary, on this table, you see that montmorillite is very high in swelling. When water gets to it, it swell like Gary, and the CEC of montmorillite is the best, is the highest in terms of highness. And what is CEC? That is cation exchange capacity. And what is this capacity? Every soil, like I said earlier, has chemical, has compound in it. The ability of a particular soil to be able to exchange the salt or the mineral that is in it with another good one is what we are talking about here. For example, maybe this particular soil is having potassium sulfate in it. And now what we need to achieve this earthing thing that we need is iron sulfate, then, or copper sulfate. It can change the potassium sulfate to the copper sulfate that we need. That is the CEC. So for the montmorillite, it's very high in swelling. And when you see the water retention, it's also high. So the earthing suitability is excellent. But when you go to highlight is low moody. And from 80 to 150 of the montmorillite, this one has already dropped to 20 to 40. It's moderate, it's fair, but it won't give you that 5 ohms that you are looking for in good in time. You need to work on it, but it's still better than kaolite. So you see, kaolinite is worse in terms of CEC. The CEC of this one is 3 to 15, very low. It doesn't retain water. It's very poor. If you see this on site, then you must roll your sleeve, get ready to work. Then we have the chlorite. That one is also low. The CEC is between 10 to 40. It's moderate. It's fairly poor. So now, which of these is now easy? From what we see from the upper slide, you can easily know that montmorillite is very okay in terms of earthing. If you meet this type of soil, it makes your work quicker and you quickly leave the site and then happy because you get your desired result in time. Why is it good? High moisture retention, high CEC, and typical resistivity that you will see in this montremonilite is between 5 to 50 ohms meter. Loamy soil, you see that one as well. So when you go down, as we begin to go, you begin to see the variation. Dry clay, the kaolite, poor retention when it's dry. And you now see the resistivity of this particular soil is between 100 and 200. So here you need to work. Remember, we are going to 5 ohms. In telecom, in electronics, is less than 1 ohm. And you are already on 100 to 200. So here it's going to take a while before you get the desired ohms that is needed, but we will get there. Then when you now go to our focus today, if the soil is dry, if it's having gravel or is stony, like the caption, the optimization of industrial earthing system designed for compacted clay-like and the soil condition. If you are here, look at the third column. Typical resistivity is between 500 to 2,000. Even the frozen part of the soil, the bank frozen, is 10,000 plus. Here, you may not be able to achieve the desired effort if you don't use the 5th generation of earthing. And that is why this is important. We need to understand the soil before we even give a quote. Even before you determine what type of earthing you want to do. And I want to send this note to us. It is the earthing system is not a rocket science. At the same time, it's not rigid. It's not one way. You can use a lot of method after you understand your soil and you also understand the environment that you want to work. So it makes it easy for you to quickly determine which type of earthing that I want to do. Is it the vertical? Is it the horizontal earthing that I want to do? Now, as a case study, as I'm bringing this to close, in no time, this environment you are looking at here now, to the left of the screen is around, this is a place around Obada. As we are going towards Abeokuta, and we are working currently there. My staff just came back yesterday evening. We are going back to the site after this short break. We'll go back to go and complete the work that we have there. So when this thing was given, we're thinking of just using the minor earthing, but the kind of conventional, something that is not too expensive because of the complaint of the owner of the work. But eventually I told him, I said, this thing that we are talking about, thank God also, as it was mentioned during the introduction, my wife also is an electrical engineer. Then we deliberated, we said, okay, it's better we do industrial earthing for these people. If not, we may run into problem because we've, like I said before, we burnt our hand before in this type of earthing. There are these work that we did sometimes ago for some company that they used to give us installation of transformer, installation of ATS in substations. And when we go there, one thing they do is that they have a template of payment. And this template of payment is... can we have audience there? Can we have audience there, please?
Engineer, please mute.
Thank you. So now we were given a template to work with. So all the earthing is the same price. There's nothing you want to tell them they don't want to hear. And we went to site. If you are very familiar with Ondo State, we are under Benizo. We were to walk along Idore Road. That is from Okiaro, around Alakara there. We have installation there. We have installation in Owo. We have installation. All of these come with different challenges. If you are familiar with that terrain, that's why they said that is the hill. People are climbing hill. So around that terrain, a lot of rocks and hills are there. And if you put mass on top of that place, you cannot have a sufficient soil, earth, to be able to do any meaningful earthing in that place, except you use this method that we are looking at today. We work at Owo. Out of the 3 sites, one of it was very tough, stubborn. Is mixture of clay and gravel, and it was very difficult to quickly achieve. Not knowing that even this particular one that I said we are working on currently is going to be tough than all of those ones. If you see the picture at the other side, this left-hand side, you will see granite, fine granite. That is the thing that was, let me see if I can expand. Then you see the borehole. This is a borehole that somebody dug last month. And all this granite you see on this place, they are the thing that came from this borehole, which suggests that where we are going to do our earthing is full of igneous rock under. And the soil is there. You don't know that there is a rock underneath the soil. The same problem this man that come to that dig the borehole also faced. He came, he brought equipment. He discovered that after drilling for just few feet, few meters, he met this gigantic rock. He began to pump and try his effort. Eventually, he got water and he packed his load and left. And the people were happy that, okay, we have water now. After 3-4 pumping, the water dry. Since then, they've been calling this man. The man has not come. Why? Because he knew what is on the ground. I told them 2 days ago, I said, you won't really blame this man. You people need to come to a round table and settle this matter. Because the water you saw initially may be the trap water on top of the rock that was trapped there. And after you pump that one, no other water except this man break the rock. So also we too that we want to dig the earthing, we didn't know that rock is under it. But what I said before we begin to look at the type of earthing we want to do here, we need to take measurement. As you can see from the picture, immediately they start this digging. Here, just a few, maybe like less than a foot. I asked them to take the reading, and they did this reading, and what we got was 132, which is 10 to clay. Is not, and we are going to 5 homes or less than 5 homes. And I told them, I said, okay, it's like this place is a little bit high, but as we go, we'll be fine. And now they dig more. Immediately when they reach 4 feet, I told them to check again. And when they check, it has moved to 704. And we are going to 5. I said, yes, this is totally different from normal soil. I'm already suspecting that there will be rock or something that is stopping the earthing under that place. So as we move and they begin to dig again, then we discover that one of the hole around this place is on 300 after a lot of treatment. What we start doing now, I asked them to begin to moisturize the soil. Let's see how far we can go with by moisturizing the soil. So when we moisturize the soil, I discovered the report on the meter is 7, that is on this meter, is 71.7. So with the enough moisture, then we have an improvement. But one of the hole that is here was so stubborn that we could not be able to even get anything less than 356 on it. So the design began to change. I told them, I said, now in this design, we can't go vertical again. Of course, we know that after these 8 to 9 feet, we already hit the rock. There's no way we can go vertical any longer. To be able to optimize what we have around now, it means we go horizontal, and this is our earthing. So we are going to change direction. If we now change the rod, maybe our copper rod from 4 feet, which is about less than 2 meters, then we change it to 2.6, maybe around 6 feet. Because we want it to go down the ground, we won't be able to go because rock is under that place. The topsoil, when you look at this place very well, is clay. When you get to the middle, it's a little bit soft. When you come down, you meet the rock. So the installation here now is the type of installation we are looking at. It's no more going to be vertical, but it's going to go horizontal. So the design here, we do a vertical to where we hit the rock, we bury the copper rod, after which we come to these 4 feet around where this man is standing, then we begin the horizontal design on it. So by the time we combine everything together, then we'll be able to get desired result. So after we begin to treat the soil, if you look at this meter, what we have there is 25.3. Remember where we are coming from. We are coming from 700 plus. Now we are at 25.3 ohms on the meter. Then we begin to now mix the bentonite and the marconite, which is suitable for the 5th generation to mitigate the high resistance that we are facing. After that, the first treatment to sample what will happen eventually. If you see this very well, you will see that we're having 17.9. This is what we are having currently. Before they left yesterday, they could not take any other reading because even the security and the staff, everyone want to go for this short break. But already we have this the mixture, the aggregate of marconite that we're going to mix with cement, that we're going to mix with water in proper ratio and to put there. If we can move from 700 plus to 17, already everything is looking green. And this is how to treat a rocky or a gravel or granite surface, ground earthen that does not permit current to pass through, that has high resistance or high resistivity. So this is a typical example, life experience of what we have. Now, I need also every one of us to also pay attention, though the meter that we have will tell us the resistance direct, and you can use that resistance to be able to know where you are. But in calculation, people can make mistake in resistivity. The calculation for conductor resistivity is different from calculation you use for earth resistivity. So you need to know that very well. If it's conductor resistivity, for example, I want to know the resistance of a copper. Copper resistivity is known. You go to the table, you check it. Aluminum resistivity is known. You go to the table, you check it. So, but you want to use it to calculate resistance. In that formula, the resistivity is the readings. That is the resistance you want to measure, multiplied by cross-sectional area of that rod or that conductor over the length of that conductor. That is what you will use, and you will get your results. But in earthen resistance is different. The resistivity is 2 pi RA. 2 pi RA, because you need the circumference of a circle to get that done. So you you need the circumference of a circle. So here you see 2 pi multiplied by the resistance that you read from the meter, and A is the distance between your rod, that you bury. Everything must be in meter for uniform units. If you now want to do standard formula for vertical rod, that one is resistivity equals 2 pi LR over ln inverse of log 4L divided by the diameter of that rod. That will give us answer to what we want. I also put here the resistance of a body, human being resistant, that can help us. I said earlier that during that conventional earthing, our skin are totally different. Skin is the largest part of the cell in our body, and also is the one that has a high resistance. Our internal organ, the blood there, inside there, we don't have up to 1,000. It's around 300, 200. But the skin can come to resistance of about 1,000 ohms, up to even 10,000 ohms. In the olden time, people that can, in the morning before 12 o'clock, they have cultivated maybe 1,000 ridges to plant yam. Their hands are tough. Some of them can take moi from the pot without feeling hot because their palms the skins are rugged. Not this Indomie generation that everything is light. We stay in the AC. We don't want to do hard job. Now we also see have more electrical component devices around us more than before. Everything from the kitchen to the bedroom to everywhere, even the phone that we put in pocket, all of it is towards this electrical situation. So our body, when it's wet, is already compromising the resistance that it has. It's around 300 to 1,000. So from the table of what we did, this is what it comes out to be. By Monday, by Tuesday, we complete and see what the result will be. But already we know that that area is a walkover thing, despite the fact it's rocky, despite the fact the surface is clay-like, but we already moving forward. The resistance, the in-homes, when we were having 132.2 ohms, the resistivity around that time was 2765. Then the estimated rod resistance that we put in the hole is around 7293.13983, like that. So this is how to actually mitigate. We get to the soil, we know what is there. We also look at, are we going vertical? Are we going horizontal? Then we also buy all those aggregates that has been produced. The only problem I have with this aggregate, if you are not conversant with it, you may have challenges. They will write 25 kilogram on the bag, but when you see the bag, when you carry it, it's not more than 10 kilogram that is there. And they are already sold for it, they sold to you as 25 kilogram. Thank you very much for the opportunity, Mr. Chairman.
Wow. Thank you so much, Engineer Fasipe Oladimeji, for this wonderful presentation. We are more than grateful. And I think now we would go straight into our question and answer section. So like I said earlier on, we can drop our questions on the chat box, or we can still raise our electronics hand so that Engineer Fasipe can take our questions. Thank you. The floor is open for question.
Hello. Good afternoon.
Good afternoon.
Good afternoon.
Yeah, my name is Babalola Olugbade. Are you hearing me?
Yes, sir.
Yes, sir. You are welcome. Please go ahead, sir.
I am appreciative to the Institute for bringing this beautiful topic of recent. I think yesterday we heard something about power factor, which is also important to our load. This one, which is acting system, it is the soul of electrical installation, that there is no test, there is no examination you will attend without making question on a earthing system. Now, I am very sorry, and I know the pain of Engineer Fasipe, who is fast in knowledge about earthing. When he looks around, left, right, and center, seeing what people are calling earthing, seeing what people are doing in both domestic and industry, called earthing system. Somebody with Engineer Fasipe, who is very good in the area like this, will be feeling sorry for people, as also I do here, even with my shallow knowledge that is not even up to his own. So well done. Well, the question I want to ask. Hello, sir.
Yes, sir.
Go ahead, sir.
Now, about the type of soil you discuss here, which are not friendly to the bearing of earthen components, I want to ask if one can use what we call conductive plus. Conductive plus is a chemical already prepared inside a bucket, especially a paint bucket, and you bury it, you make hole for it, and you bury your heart inside it. I've been using it, so I don't know what is your feeling about that, whether it has any that can make you to go for serious looking for good soil. That is one. Two, what is the permissible earth reading? Two, how often is our bury it once and you leave it there once and for all till Jesus come? Four, we are talking about salt, sulfate, potassium, whatever. Well, I know about it and I welcome it. But what do you say? Because that is what is rampant. I have it on our platform. There is this question on platform that I'm asking my fellow engineer, that is it right to use sodium chloride to bury hearting system? Those are the 4 questions I have. Thank you.
All right, thank you. Engr Fasipe, please go ahead with your response.
Yes, thank you, sir, Baba. God bless you, sir. Yeah. And I also appreciate your contribution all the time on the platform. Though we may not comment, but we see your effort, things you post, and all of that, your concern for our work. Thank you very much. Now, if we take it without wasting time, number 1 question is the type of soil. And we are looking at conductive flows. I said it in the presentation that we don't have any particular order. We don't need, at this junction, we don't need to cram anything. We are already at age that people don't assume or take things as it is come to them. We should be able to think out of box. What do we need to do? Fundamental is key. What we need is paramount. What do we need? And it's part of the question that you also asked, what is the permissive or permissible earthen reading? I said earlier, I said mostly all over the world is less than 5 ohms. If you get anything less than 5 ohms for industry, you are all right. But in communication, when we have sensitive gadgets, if the resistance of the earthing, if it's up to 3, there will be humming. Videos will be waving. Communication line will be disrupted. So based on that, the permissible reading of the telecommunication is always less than 1 if you want to get a smooth running. But in general, anything less than 5 ohms is all right. That is it. So now to use conductive plus, there is nothing bad in it if it meets that requirement. If you can put the earthen rod, the copper rod, whatever you put in it, and you take your reading, and it's giving you that desire less than 5 ohms. That equipment that is connected to that earthen bar will be safe.
I can hear you.
For example, look at the upper slide of my show where these consoles are. Hello. This is a bar where all earthen wire or conductor meet. Immediately you test and you see that the readings is less than 5 ohms, you are okay. But do we leave it forever till the loss come? No. Earthing is to be checked periodically. Periodically in the sense that season changes. And we know that we need moisture, soil, ground, earth to be able to get these things that we are talking about, these readings, these desired ohms that we need. So you don't just leave earthing and leave it permanently forever. You don't leave it like that. You go to check. That is why in earthing construction, you create a part in your construction like a breaker that you will break from the system. When the system is not in operation, you will switch off the remaining connection. Then you will not take your reading to know whether that earthing is still all right or not. In some design, we also create pipe, PVC pipe, that will lead out of the pit, where we can be topping water. Some area, we create this funnel like from the roof to create a kind of reservoir that will also be watering. Like, sorry, I'm a Yoruba man. Don't sọ pé tójò tẹrùn, ilé alákàn kì í gbẹ. The bedroom in the village, if they want to plant sugarcane, they go and plant it there. If you want to plant some vegetable, you go and plant there because you know that somebody the water will come. So we create a kind of reservoir like that to keep watering, moisturizing the soil. So the question 4. So number 1, conductive is okay if it meets up the required readings. The reading should not be more than 5. Number 3, how often? We go to check periodically. Isolate the whole system and take your reading. Number 4, is sodium chloride all right? The way people use, no. It's gypsum salt that is even good for earthing in the first place. Both the sodium chloride and gypsum salt also, they have their problem because they will corrode the metal. That is why the conventional, when we explained that it has a limitation. It causes corrosion, especially even sodium chloride. If you put your spoon in the house there, it will corrode. It's not good for earthing. Now that we are even having more sensitive equipment and gadgets, it's better we use aggregates that will not corrode. Thank you, sir.
Thank you, sir. Please, can you drop your phone number?
All right, sir.
You will have it on the platform, sir. Oof.
Okay.
Thank you, sir.
Thank you. Yeah.
All right. So, Engr Fasipe,
all right, sir.
I have one question from somebody that says that that's Engr Onoja. For the vertical to horizontal, if you get to the rock on the horizontal, what can someone do?
Then you go vertical, like I said. Now, what do I mean by vertical? Now you don't use rod any longer because the rod will not be able to penetrate any longer. What you do now, you have earth mats. Like that design, can I go back there? What we are planning to do? Now, if you look at this place, if you look at this place, we already segment this pit now. We have this base about 4 to 5 feet. Then we have this depth where the earth rod is going to be. All this is 5 in number. It's 5 in number. Now the rods will come inside all of this. Out of these 5, the one that is around this where my cursor is already at 300. I think the rock there comes up more than others. So this one, I'm not expecting to get so much from here. What I will do here at the end of the day is to create a pipe where I will be injecting water during dry season here. The hole will not be useless like that. So now, from this place now, we are going to put earth mat here. We are not going horizontal down again. Then we are going to create more parts here that we are going to put earth tape. Not earth wire now, earth tape. We are going to put it on the earth mat, and we send to the second hole that is beside of this place. So it will link this pit together with the second pit. The second pit also will carry the mat. This one will carry the mat. They will go horizontal like that. We keep testing, we keep moving until we now use the aggregate of what we can get along the path of the horizontal. From this pit to another pit, we link all of it together. That is the horizontal movement. And what we use that time is no more rod, it's earth mat and earth tape, linking all those mats together. And each hole also is treated with these gems, the aggregates. There's no way you will do all of that before you know you're already having like 2 homes. That is perfect for what we are looking for. I don't know if I've been able to answer, Engineer Onoja.
Yes, I think you have done justice to that question. So, do we have any further question?
Yes, sir.
That's 500,000.
All right, please.
Yes, sir.
Can we have your question?
Okay, thank you, Engineer Fasipe, for this insightful presentation. My question will be, for us who are into building services, renewable energy,
For what?
sometimes we do, for us who are into build services,
Okay.
build and renewable energy, where we need to work on existing facility and they need to do earthing. And all the floors are being concreted. Of course, you know that we need to do the soil test before we even give them a code, just like you mentioned. And then for most of those installations, you know, they are looking for low budget earthing installation because they realize that what they are installing just needs earthing, and they will not want to go to spend so much on earthing. Now, for the floor that has been concreted, would you advise us to start breaking the whole floor, or is there a fail-proof method we can use once and for all to achieve at least something close to 5 homes? Because in that instance, you may not be able to do horizontal earthing, breaking from one point to another, especially when you don't know what is being what was on the floor there. If you have a very restricted work area, so what would you advise in that regard? Thank you.
Okay, thank you, sir. So what's the name again, sir?
Engineer Fasipe.
Okay, Engineer.
FinSec.
Okay, sir. Okay, sir. So, like part of what we've mentioned now, if you look at what the diagram, what we discussed, and what Baba Olugbade asked, what he said, is that has solved this question. If we have restricted area and the people also have low budget, what we need to do is to work with their budget, because at this junction, I won't say if the client cannot pay so of million, we should reject the work. No, we don't need to reject the work. We need to improvise. And that improvisation is what, if you see what Baba mentioned, this conductive plus is in a bucket of like 20, is it up to 20, like 10 liters, some like 20 liters pay. You understand? The earthing system can be there. That is what he said he has been using. Now, if you look at that picture that was displayed, it's like we are having restricted area already. We already imagine our mind that we don't have the depth any longer. We want to work within the space that we have. So for this solar system and installation, what you need to do, if you are permitted to get 2 by 2 feet on their ground, is enough to do whatever you want to do. Even 1 foot is also can do a lot. Go to the depth you can go to, but have at the back of your mind that we are going to do backfilling. It's backfilling that will solve it. Instead of returning the earth that we excavated after you have your 2 feet, like 60, it's not even up to 600 by 600 ties that you need. After you have that one, you will not use the earthing that you remove from it. You are going to use the aggregate to fill it up. in between that space that you have. So by the time you have that, and you have also a portion where you can be injecting water periodically, you will definitely get that result that we are talking about. So we don't need much space in some cases. And of course, you know that your hands are tight and you don't have the fund to go extra mile. You don't have the space to go extra mile. That is where reservoir, pocket, and a narrow pit comes to play. Those installations around the rock, around those idori that I mentioned, even in the desert, pure desert, that is sandy, there is no anything you want to do there that want to answer you in time, because water is not staying. Everywhere is dry. The sun is hot. So you need to inject water and also create a pocket-like pit where you can put those aggregates to help quick resistance reduction. So that's what we do. Thank you, sir.
Thank you very much, sir.
All right, thank you, Engr Fasipe. Do we have any other question? The floor is still open for contributions and questions.
Hello, good evening, engineers.
Good evening.
My name is
Yes.
Engineer Noja. Actually, I wanted to ask a question concerning in a building whereby someone must have done all his installations, and the facilitator said we should be able to find a way to make sure that that place is always wet. Is it advisable to connect a building AC, that's the drain of AC from the building, connect it into the channel into the earthen pit, so that we make sure that that place will always be wet? Is that advisable that way? That is one. Secondly, when I was going to ask a question concerning the vertical and horizontal earthing, when you were explaining it, please, I could not, my network on my area was very bad. I don't know whether I can go through that again. Thank you.
Okay. The start second one. What do you say? The one you said you could not get.
The horizontal to
all right, all right, all right.
By the time you meet a rock, what
no
do you
problem.
do?
I get it.
Okay.
So now,
all right,
the explanation. Let's start from that explanation. I will still use this, what we have here, to explain. Now we have met rock. Maybe you can see my console on the screen. Can you see the console?
Yes, it can be seen. I can see.
Okay,
it.
now, so what actually happened now is this layer, this pit, the design here is of 3 layers. The upper, this is the second layer where this man is standing, and the third is the third layer is the one that is down. So the rod is inside this down one. Then under here now, after 5 feet, rock is there. We stop. So what we do now, after we are stopped on this vertical, we now go horizontal. Yes. On this place now that we cannot put rod, we use copper mats. So when you put copper mats here, you have another hole now, another pit beside it. You are going to treat it with all the aggregate the same way you treated this one, and you are going to put copper mats there. Then you now use copper tape to link this pit together with this pit. Then you continue to go and take your readings. Before you will do 2 or 3, you will be fine. And that is the horizontal way of movement. Okay. It's understood. For the AC, it's fine. It's for the fine. AC. Since the AC water is not having chemical, I don't think it has one. It's just the still water from the evaporation from this AC gas that is cooling the inside of the house. So it is that evaporation that causes cooling that bring about the water. It's like a steam. I don't think it's having any harmful chemical. It's better to put it there to save one from looking for tap water or well water where there is no one. I think
I've encountered so many situations whereby before I dig 2 feet down, I encounter water, especially in waterlogged area like Ajawo Estate, Okwebi, and the like. So, and I will not be able to dig further because the further I dig, the further the water comes from below the ground. So what would I do, or what would you advise in such soil condition? Thank you.
Okay, sir. Like we said, the way we answered the first one is still the same way we answered this second one. Since we don't need too much of water, the environment is also still going to be customized to what we want. In that area, like I said, it's not rocket science, or it's not a particular, it has to be this particular way. If you can get a reservoir, if you can get something like, how do I say it now? It's also a reservoir that will say when you mold block on site, where you put your water in during when they are building, where tanker drop the water, not inside the plastic. Now, this concrete four-corner wall thing that is constructed like soccer way, it will do this thing. Water will not be able to enter. If you can dig up, fine. If you cannot dig up, raise the block up. All we just want to get is to get that 5 ohm less or less than 5 ohms that we need. And since you are going to backfill, you are going to also add other earthing material to help to improve the soil that you have inside that place. You will still get the required results. But the thing is, the way you will be checking is different from when you are in a natural place. You need to check periodically if the resistance is still where it is. If it has changed, maybe increased, then you treat again, then everything will be fine. Since you cannot dig more, you can raise your block. You can put the pocket, like we said earlier. All of this is possible. All we just want to do is that the resistance of where we are sending the earthing is not higher than the equipment or the operator. It has to stay below 5 ohms.
All right, Engineer Fasipe, thank you. In addition to that, Engineer Hafiz, he has made it clear, when it comes to acting, it's just relativity. If you check our charts, there are so many types of soil that you can come across. You believe that even inside seawater, we can do acting. Inside the lake or brook water, we can do acting. The major thing is to take cognizance of what he has said, your typical resistivity in this area, and your usual limit in terms of resistivity. You need to take cognizance of that so that you know that you are safe in any type of installation that you are doing in such environment. Thank you. So I think we can have the next question.
What I would like you to add is some of the experience you have in variance of this acting parameter as time goes on. What are the causes? After, whether in some years, you now check, you are having a bit of variance from below 5 to 6. What can be the relative causes of all these things? And what should we watch out for? Even when we go to site and we find something that might at least affect our acting installation. Thank you, sir.
Thank you, sir. Engineer Benga. This is a very important question that we also need to check. Most of the earth rod that we have in the market that we call copper, they are not copper. They are copper coated. Some of them are iron, some are steel, some are brass. So when you have all of this, there is possibility of this coating to erode. It can be one of the causes whereby at the end of the day, the conductivity will reduce. The reason why we are talking about copper is because we know that copper is a good conductor, or let me say a better conductor than aluminum and the rest. Those that are also still better than copper, they are rare and they are expensive. So copper is what we settle for. And most of these things we use are coated. They are not original copper in most cases. So as those coatings give away, it can compromise the conductivity of the soil. I mentioned earlier that seasonal changes affect the moisture of the soil. This is also what to look out for. The environment where we are doing this earthing, if it's the one we already know that is having rock under it, or is in the desert, during the dry season, everywhere is dry. There's possibility of not having enough moisture that can aid the earthing. So we need to go to check and see the condition of our earthing system. The rocky area that may not have access to enough water as well, after some time, we may still need to go to check. So what the thing we need to, the condition that can make the earthing value, the resistance of the resistivity of the soil to increase is those things that I mentioned, and the like that. Some environment, industry, maybe they produce chemical and they have spillage. If they have spillage, there's possibility that some of their chemicals percolate, linked to our system installation, then it compromises the chemical constituent of all that we have before that make us get what we get. Those situations again, we compromise. So if we see all these signs, dry season, chemical lynching, all of that can cause the resistance to shoot up. And then we need to go back and find how to improve it back. Thank you, sir.
All right, thank you. Engineer Yemi Adeleke, please, can we have your question? Your electronic side is up.
Hello, good afternoon, sir.
Good afternoon.
Good afternoon.
Can you hear me, sir?
Yes.
Loud and clear. Please go ahead, sir.
I want to appreciate you and Engineer Fasipe for your well-detailed lecture.
Your name, sir?
And though I joined late, I was one that requested for your soft copy.
Yemi Adeleke. Yemi Adeleke.
Sir, can you hear me?
Yes, please.
Okay, my question is, can we get zero in arting? Can we have zero in arting? Because there was a project I handled in Ibadan. So after the project, we got a very high value, maybe 26 or 6, was an estate. So later we introduced some arting material, bentonite and some other things. Then we dig deeper. There I understand that Ibadan is a very rocky area. We dig deeper. So we put on bentonite and some other things. But that time I got the experience about what the bentonite is and everything. So after the whole thing, I got 0.00 something. So when I now reported my case, so the senior engineer that gave me the job, I said I got I got zero. He said, shut up. How do you get zero? How do you get zero? We can never have zero. So later I now reveal the whole thing, but it's 0.00, maybe 0.03 or something. And then that's better. But so I want to ask you also, do you subject to that we can never be zero? It's not conventional for you to declare zero.
Engineer Adeleke, that's why I laugh when you say zero. I say zero. How? The same way the other guy reacted is the same way I reacted when you say, can we get zero? It doesn't really make it. It can be 0.0.
Yes.
And during the lecture, I said, for telecom, sensitive equipment, when you're having radios, communication, gadget, and all of that, you need less than 1. And if it's less than 1, it's 0 point something. So that is possible. You have to. It's because you came late, or maybe I did not mention Ibadan. These are the area you need to watch out for. Ibadan is rocky. Ondo State, yes. Prepare your mind very well. Ogun State, around Abeokuta, you have to roll your sleeve. So what you did there is what is needed, is the 5th generation earthing that you need to do, and that's what you have done. Maybe because of the fear of the value that you got, you did it.
I got 0.03. I just had a 0.0.
You did it with aggression, so that the thing will fall, and it fell.
I now open the whole thing. I now show it on my map, my clamp meter, and I saw okay. Now for the half meter, they have declared the whole value. 2 kilogram something.
Maybe before.
Now that's better.
Yes, maybe you approximated before your machine.
Yeah, I approximate, and I wanted to get on him. Say, I got shut up.
So it's good that way. Thank you, sir.
Yes, sir. Thank you, sir. I just wanted to laugh on me.
All right. Thank you so much, Engineer Yemi Adeleke, for your question. And as well, Engineer Fasipe,